Hello and welcome to today's lecture on synthesis for low power, a new VLSI design paradigm for DSM. Here DSM stands for uh, deep submicron technology. As you know, nowadays the VLSI circuits are fabricated by using 40 nanometer technology. So obviously it is very small compared to 1 micron. That's why it is called deep submicron technology. And this is the outline my talk. First I shall discuss why low power, then I shall discuss about various sources of power dissipation, then what is the degrees of freedom in this context, then I shall discuss about low power synthesis techniques, particularly how to reduce dynamic power reduction and how to reduce leakage power. So these two we shall discuss. So let me first start with why low power. You know, until recently performance has been synonymous with circuit speed or processing power, for example MIPS and megaflops. As you know, until recently the VLSI circuits were synthesized for higher and higher performance. The processor performance was stated in terms of million instructions per second, that is MIPS, or million floating point operations per second, that is your megaflops. So speed was the primary consideration until recently. However, power consumption, I mean in those days power consumption were of secondary concern. People were not bothered how much the power consumption is taking place in the VLSI circuit, and actually as a concept it was not really important in those days because power consumption were not very high. But recently what has happened in nanometer technology, power has become the most important issue because of several reasons. Number one is increasing transistor counts. As you know, based on Moore's law, the number of transistors is increasing, I mean by 1.5 times almost every year. So number of transistors is increasing. Now you can put several million transistors on a single chip. Obviously more number of transistors are there will be more power dissipation. Secondly, as we shall see, the power dissipation depends on the speed of operation. That means when the frequency of operation is increased, power dissipation increases. For example, in the early years the microprocessors were operating at in the range of megahertz. Clock frequency was several that megahertz, but now clock frequency is gigahertz, and as a consequence the power dissipation has become very high. Thirdly, because of deep submicron technology, later on I shall discuss about it in more detail, the leakage power which were not present in the earlier microprocessors or VLSI chips has become very important. So leakage power is increasing at a very large rate. Lastly, increased process parameter variability due to aggressive scaling has created problems in yield, reliability and testing. What has happened, you know, whenever the dimensions become smaller and smaller, small variation in fabrication process leads to large variation in the parameter of the device. For example, there will be various process parameters like the leakage current, the threshold voltage, then your length of the device, width of the device. These values varies, and because of these variations, yield is reduced, reliability decreases, and testing becomes difficult. So these are the issues which are becoming very important. That's why low power is becoming very important in the present day context. Let us have a look at contemporary high performance processors, and you will find that they consume very heavy power. Let us look at the different microprocessors which were introduced in different years. Here only Intel microprocessors are shown. As you can see, 386, if you consider power consumption is little more than 1 watt. If you go to 486, it comes to 5 watt. If you go to Pentium, it comes to about 15 watt, but as you go from Pentium to Pentium Pro, Pentium 2, Pentium 4, you will find it is touching 100 watts. So 100 watts power dissipation is taking place from the microprocessor. And obviously, cost associated with packaging and cooling of such devices is prohibitive. That means whenever the heat is dissipated, you have to take out the heat from the chip, otherwise it will fail. So packaging and cooling is very important. You have not seen in our institute, we had a mainframe computer, Cyber, Russian computer. The power dissipation was so high that it has to be cooled by using chilled water. So we had to set up a chiller plant, then the chilled water has to be circulated around the processor to keep the processor cool. So that means the packaging and cooling cost is prohibitive whenever the power consumption is very high. And so what is the alternative? Alternative is we have to adopt low power methodology to reduce the cost of packaging and cooling. Otherwise, cost will be so high that the one claim of Moore's law is that cost will also decrease. Obviously, cost will not decrease if the cost of packaging and cooling is very high. So, to reduce the cost of packaging and cooling, what you have to do? You have to develop suitable low power design methodology so that the power consumption is reduced. Second, as you can see, another very important parameter, that is your power density. What is power density? Power density is power dissipated per unit area, watt per centimeter square. Dimension of the transistors are reducing. The number of transistors over a particular area is increasing. As a consequence, power dissipation, power density is increasing at a very alarming rate. And as you can see here, if you consider the various processors, 8080 start, what was the first microprocessor? 4004, that was introduced back in 1971. And subsequently, as you can see, other processors have been introduced, and the power dissipation was not very high until it was Pentium and Pentium 6. You can see already the power dissipation has touched the power density has touched the power density of hot plate. What do you do by using hot plate? You do cooking. So there was a cartoon in one magazine that there is a cyber cafe. So people are going there to surf for surfing, and then on top of the processor they are frying eggs. So fried eggs are also being supplied. That's a byproduct. So that's a cartoon. But you can see the situation is that power density has already crossed the hot plate, and unless it is stopped, it will touch the power density of nuclear reactor, it will touch the power density of rocket nozzle. Obviously, it cannot be allowed. So only alternative is to adopt low power design methodology. Now, there is another reason for low power. You must have observed the emergence of portable computing and communication equipment such as laptops, palm tops, desktops, cell phones and whatnot. So, number of such battery operated portable devices is increasing at a very high rate. So, there is a proliferation, high proliferation of this type of devices. Number of such portable devices which are manufactured is much more than the number of desktops or servers or workstations. And obviously, in such cases, since these are battery operated, battery life is of primary concern. But unfortunately, what has happened, the battery technology has not kept up with the energy requirement of the portable equipment. You are incorporating more and more functionalities, you are making it more and more powerful. For example, in your cell phones nowadays, you have got not only you can talk, you can take picture, you can send message, and you can do all sorts of, it's a kind of computer. You are keeping on increasing the functionality. What is the net result? Power dissipation is increasing, power consumption is increasing, but the battery that you are using is that technology has not improved at the same pace. So battery is not able to sustain the necessary power requirement. although there is some improvement in battery technology, but it has not kept up with the energy requirement of the portable equipment. So in such cases, commercial success of these products depend on weight, cost and battery life. Whenever you go for buying a cell phone, what do? It should be lightweight, it should be small, it should sustain 3 days after charging. These are the conditions you will apply. And obviously, sellability of a product is dependent on these parameters: weight, cost and battery life. And obviously, in such cases, low power design methodology is very important to make these battery operated devices commercially successful. So these are the reasons for low power, particularly in battery operated systems. And as a consequence, you will find that some synthesis technique has emerged which are battery aware. The characteristic of the battery has to be taken into consideration while designing a digital system, which were not done earlier. Because battery is there, it will be used, people were not bothered about how long it will give power and so on. So, but now it has become very important, battery aware synthesis it is called. So we have to use battery aware synthesis technique. And another important concern is reliability. Reliability is closely related to power dissipation, and it has been observed that every 10-degree rise in temperature roughly doubles the failure rate. Why? You will find that there are a number of failure mechanisms. For example, silicon interconnect fatigue, package related failure, electrical parameter shift, electromigration diffusion, junction diffusion, gate dielectric, thermal runaway. I am not going into the details of these mechanisms or phenomena, but because of these phenomena happening within the chip, the processors will fail. And as you can see, as the temperature rises, say close to 100 degree, little less than 100 degree above normal operating temperature, various failures will start happening. And obviously, you have to, if you want a reliable chip, the temperature should be low so that the failure rate will be lesser. That means you have to develop suitable methodology so that power dissipation is low, leading to reliable processors. Finally, coming to the environment, according to an estimate of the US Environmental Protection Agency EPA, it has been observed that 80% of the power consumption by office equipment are due to computing equipment, and ironically a large part of the equipment are not being used. You may have seen, not now, earlier if you visit an office you will find computers are on, but nobody is using. That was the scenario. And in fact, whenever the system is on, power is dissipated mostly in the form of heat, and what you have to do to take away the heat, you have to use cooling technique such as AC, air conditioner, and you have to, what the air conditioner does, it takes the heat from the room and releases to the environment. So it leads to heating up of the environment. So to reduce adverse effect on environment, such as there were some efforts such as EPA's Energy Star program leading to power management standard for desktops and laptops has emerged. Nowadays you will find that if you don't use a laptop or a desktop for certain duration, it will automatically shut down the screen, it will shut down some of the internal power hungry circuits, so it will reduce the power dissipation. That has emerged because of this Energy Star program. You are getting the benefit of it. This is essentially a low power technology that has been used. So shutting down some of the subsystems where they are not in use, and this has obviously reduced the power dissipation of the offices. So you can see we are nowadays very concerned about our environment to save the planet. So here low power design methodology in a direct way helping this protection of environment. So I believe even now convinced that low power design methodology is important in the synthesis of VLSI circuits. Now I shall discuss about the technology which is used in realizing VLSI circuits. In this particular course already fundamentals of CMOS circuits has been introduced to you, and you know basic ideas about CMOS. And CMOS is the technology that is being used nowadays in realizing VLSI circuits. Although other technologies are emerging, like various exotic techniques like optical computing, quantum computing, but they are still in the research stage. So CMOS is the technology that is being used in realizing VLSI circuits nowadays, and it will continue to be so in the coming years, at least in the foreseeable years. So you have seen CMOS has emerged as the technology of choice for low power applications, and it is likely to remain so in the near future. Here is a schematic diagram of a CMOS circuit. As you can see, here you have got essentially two blocks, you can say NMOS block, which are pull down devices, and PMOS block, which are pull up devices. So PMOS transistors used to realize the PMOS network, and the NMOS transistors are used to realize the pull down network. And in any CMOS circuits, this will be the basic configuration. And as you can see, the CMOS, this is the example circuit, which is nothing but a 3-input NAND gate. So this 3-input NAND gate has got 3 NMOS transistors and 3 PMOS transistors. And in this type of CMOS circuits, the power dissipation can be broadly divided into two types. One is dynamic power. Dynamic power again comprises three components. It consists of switching power, short circuit power, and glitching power. I shall briefly tell about these three power dissipations. And there is static power dissipation. Static power dissipation is not, conventional static power dissipation is not present in CMOS circuit. As you know, in CMOS circuit, either the PMOS transistors are on or NMOS transistors on, or there is no direct current path from the power supply to ground. That's why there is no conventional static power dissipation as it is present in NMOS, TTL, and other types of circuits. However, there are various types of leakage currents. I shall discuss about various types of leakage currents. Some of the important sources of static power, which are essentially leakage currents, are shown here: band to band tunneling current, subthreshold leakage current, and gate oxide tunneling. So these are some of the leakage currents. I shall give some more names later on. So first let us consider about the switching power. So what is switching power? This is one of the sources of dynamic power dissipation. What do you mean by dynamic power dissipation? When the circuit is on and you are changing the inputs. Your clock is changing, input is changing. That means you have applied the clock if it is a sequential circuit, and you will see that there are some combinational circuits also like dynamic CMOS, which also requires clock. And also inputs are changing. When the inputs change, outputs also change. And as a consequence, you can see this is our CMOS generalized block diagram of a CMOS circuit. Here you have got pull down network realized using NMOS transistors, and pull up network realized using PMOS transistors. And here you can see there is a capacitor which is connected to the output, which is CL. This is not really a lumped capacitor that you have connected to the output. These are essentially the intrinsic capacitances present in CMOS circuits. That means gate capacitance and various other capacitances. And as you can see, whenever you charge, whenever output changes from 0 to 1, there is this capacitor gets charged through the pull up network, that means through the PMOS transistors. And similarly, whenever output goes becomes low, I mean goes low from high, that means switches from 1 to 0, then that whatever energy that is being stored in the capacitor gets dissipated through this pull down network. That means what is happening here, while charging, power is dissipated in this pull up network, and some of the energy is stored in this capacitor CL, and this whatever energy that is being stored in this capacitor CL gets dissipated in the pull down network whenever the output changes from 1 to 0. So while charging and while discharging, that means if you change change the input combination and such that the output changes from 0 to 1, then the capacitor will charge through the PMOS network, and if you change the input combination such that output changes from 1 to 0, then this capacitor will discharge. Because of this charge and discharge mechanism, there will be power dissipation, and this power dissipation on this load capacitance is represented by alpha L CL into VDD square into F. You see, VDD is the supply voltage, F is the operating frequency of the circuit, CL is the load capacitance, and alpha L is known as the switching activity. You may be asking where from this factor is coming. Actually, the output does not change at every clock. So you have to take into account that factor, that for a particular circuit, the output will switch for some input combination, it will not switch for some input combinations, and as a result, that means the output will change. The number of changes will be less than F. F is the number of transitions per unit time, that in 1 second. So many transitions will not take place, it will be less than that. So alpha L will be less than 1, maybe 0.3 or 0.2 depending on the circuit. So this is the power dissipation in the load capacitance. However, inside the circuit there are other capacitances. For example, here I have shown you a NAND gate. Apart from this load capacitance, you will see there is an internal node capacitance which is at the junction of these transistors Q4 and Q5, and here also another capacitance, intrinsic capacitance is present between the transistors Q5 and Q6. So between the source of Q6 and the drain of Q6 and source of Q5. So there will be power dissipation in these capacitances as well, because there will be again charging and discharging that will take place. So to take into account these power dissipations, we have taken another factor. You can see this part, that alpha I, which are essentially the switching activity at an internal node I, Ci is the capacitance of that node I, VDD is the supply voltage, and here we have not taken, this is not VDD square, but here it is VDD minus VT. Unfortunately, that factor F is not here, it should be there. So there is a correction, F also will be here. That means alpha I Ci VDD into VDD minus VT into F. So please take note of that. Second thing is, you may be asking why it is not VDD square here. The reason for that is, you will find that here the voltage does not charge to VDD, because there will be some drop across this transistor, and that drop is VT. That means voltage will charge to VDD minus VT. That is why the power dissipation is at these internal nodes will be VDD into VDD minus VT instead of VDD square. Okay. So this is the expression. Try to remember this expression. You can see here, because whenever you will be trying to reduce power dissipation, you have to essentially reduce some of these parameters. Either you have to reduce the switching activity alpha L, or you have to reduce the capacitance CL, or you have to reduce the supply voltage, or you have to reduce the frequency F. That is how you can reduce the power dissipation. In other words, you have to know your enemy before you try to fight them. So that means before fighting your enemy, you have to know about your enemy. So these are your enemies. Second source of power dissipation is short circuit power. What is short circuit power? Short circuit power is, as the input change, normally, as you know, we have seen For example, in this case of inverter, when this input is high, output is low. Input is high, then this PMOS, NMOS transistor is on, PMOS transistor is off. And similarly, when this input is low, the NMOS transistor is off and PMOS transistor is on. So, at any instant of time, none of the two transistors is on simultaneously. But if the input changes slowly, then what happens when the input in this range, which is greater than the threshold voltage of the NMOS transistor, and it is less than VDD minus the threshold voltage of the PMOS transistor. As you know, the threshold voltage of the PMOS transistor is negative. That is why you have taken the absolute value of the threshold voltage of the PMOS transistor. So, that means whenever the input voltage is in this range, then this transistor is on as well as this transistor is on. That means both the transistors will be on whenever the input voltage is in this range VTN, I mean greater than VTN, less than VDD minus VTP. So, what will happen in such a situation? The VDD will be connected through these two transistors to ground, as if VDD has been shorted to ground through these two transistors, and this is known as short circuit power dissipation. That means short circuit power dissipation takes place only when the input changes slowly and input is in this range. That means which is greater than VTN and less than VDD minus VTP. And the expression for short circuit power dissipation is given here. I mean the current is short circuit current is given here. It is 1 by 12 into K, which is a constant, which is actually dependent on the length, width of the transistors, then you know that mobility of the transistors and so on, those parameters, the thickness of the silicon dioxide of the transistors. However, it depends on other parameters like supply voltage. As you can see here, you have got VDD minus VT cube. That means if you want to calculate the power dissipation, you have to multiply this with VDD, and if you multiply with this VDD, you can see this is proportional to VDD minus VT cube. That means VT is the threshold voltage of both the NMOS and PMOS transistors, which has been assumed to be equal here in this case. That means VT is equal to VTN is equal to VTP. Now, we find that this power dissipation is dependent on the supply voltage, heavily dependent, because there is a cubic relationship. It is dependent on the frequency of operation. It also depends on tau. What is tau? Tau is the rise time and fall time of the input signal. That means if it rises slowly, then there will be more short circuit current that will flow, and if it falls slowly, rise time and fall time is slow, I mean is longer, then the power dissipation will be higher. This current will be higher and power dissipation will be higher. That means it is dependent on supply voltage, it is dependent on frequency, it is dependent on rise and fall time of the input signals. So, to reduce short circuit power dissipation, you have to control or rather minimize these parameters: supply voltage, frequency of operation, and rise and fall times. Coming to the third type of dynamic power dissipation, that is your glitching power. And normally, as we assume that the gates do not have any delay, zero delay, but in reality that is not so. The gates will always have some delay, and because of delay, what can happen is illustrated in this simple circuit. Here, as you can see, for input combination 101, what is the output? Output is low. 101 if you put, then output will be low. Again, for input combination 000, output is also low. That means if the input changes from 101 to 000, output should not change, it should remain 0. But unfortunately, you can see here this gate has some delay, this gate has some delay, and as a consequence, for this input combination 101, this output this output should be 0, and it remains 0 for certain duration because of the delay of these signals passing to this, and as you can see, it remains 0. It should have become 1 for this input combination 000, but it rises after some delay because of this delay of this gate. Similarly, and as a consequence, for certain duration, for this duration, for certain duration, the output is here, input combination is such that output becomes 1. So, you get a kind of which we call glitch. Glitch means which should not have happened, but has happened because of the finite delay of the gates. That means, here we find that output is becoming 1 for a very brief duration because of the finite delay of the gates of this circuit, and this is known as glitching power. And we have already seen that whenever the output changes from 0 to 1 and then 1 to 0, there is power dissipation, because there is some capacitance associated with this output, and that output will be charging and discharging, and obviously there will be power dissipation in the NMOS and PMOS transistor network within these gates, and this leads to glitching power dissipation. And nowadays the glitching power dissipation is not very small. It has been found to be close to 20% of the total power dissipation in CMOS circuits. Okay, coming to leakage power. So there is a landmark paper by Kaushik Roy and his group. Kaushik Roy is one of our ex-students who is professor in the University of Purdue, and he published a paper, and where he has given the leakage current mechanisms. Various leakage current mechanisms have been given in detail in deep submicron technologies. Here you can see this is a MOS transistor. I believe you are now familiar with MOS transistors. You can see here there are various leakage currents, I1 and I2. These I1 and I2, these currents are taking place in the junction of the diodes. As you know, if we consider this is a NMOS transistor, this will be N plus region, and this is substrate, this will be P. So there is a diode here, this is N plus and this is P. Similarly, this is N plus and this is P, and these diodes are reverse biased. And since they are reverse biased, as you know, reverse biased diodes has some leakage current. So there will be reverse biased PN junction diode leakage current. And another phenomenon that is happening, which is known as band to band tunneling current, because of the smaller dimension of the device, the electrons of the valency band will go to the conduction band of the N region. That means electrons of the valency band of the P region will move to the conduction band of the N region because of voltage, in electric field, because of the voltage drop across these diode junctions. So these two, I1 and I2, are essentially known as junction leakage currents. One is due to reverse biased PN junction diode leakage current, another is band to band tunneling, because the electrons are moving from valency band to conduction band, and that is why it is called band to band tunneling current. And this band to band tunneling current is becoming predominant in deep submicron technologies. Then the third source of current, which is also very high, that is your subthreshold leakage current. As you know, normally we assume that whenever the gate voltage is less than the threshold voltage, there is no leakage current, no current passes through the channel. We assume that because channel formation has not taken place, so there is no possibility of current passing through it. But unfortunately, that is not true in deep submicron technology. Even when the input voltage is less than the threshold voltage, there will be substantial leakage current, particularly if the gate voltage is close to the threshold voltage, and this is known as subthreshold leakage current. Then you have got currents through the gate oxide I4 and I5. I4 and I5, these currents are due to essentially two mechanisms. One is known as gate oxide tunneling. As you know, later on I shall discuss, you will find that as you are going from one technology to the next technology generation, we are reducing the width of the silicon dioxide. That means the width of the silicon dioxide is becoming thinner and thinner and thinner, and now it is only layers of few molecules. And whenever it is a layers of few molecules, electron will pass through the that insulating layer. Normally we consider gate input impedance is infinite, very high, but in reality it will not be so, because the thickness is very small. The particularly electrons, because of their higher mobility, they will cross that silicon dioxide layer, and this leads to gate current, gate leakage, that is your gate oxide tunneling current. Second phenomenon is due to, again that is also due to gate oxide, because of high electric field, particularly electrons will acquire very high energy, and whenever the electrons acquire very high energy, we call it hot electron. These hot electrons again will cross the silicon dioxide layer, leading to leakage current, and this is due to gate oxide leakage current. So, these two are essentially gate leakage currents. Then we have got channel punch through. Channel punch through arises, there is a depletion layer here and also here, both around source and drain. But whenever the dimensions become smaller and smaller, these two depletion layers may touch each other. Normally it should not touch, but it may so happen because of smaller dimension, these two depletions layer will charge and leading to current passing through the through the circuit, and this is known as channel punch through. As if these two, the depletions layer, have touched, some kind of punch through has taken place. Lastly, it is gate induced drain leakage current. Because of higher gate electric field, there will be a drain current, and this is known as a GIDL, or gate induced drain leakage current. So, these are the various sources of leakage currents. These are becoming very predominant in deep submicron technology. For example, this is your that PN junction reverse bias current, which I have explained few minutes back. You can see these are the diodes. This is the P region, this is the NMOS transistor N, and this is P region NMOS transistor. So, you have got reverse bias diodes. Here also you have got, in that P transistors, you have got reverse bias diodes, and you can see within the geometry of the device you have got several reverse bias diodes, which currents will pass through them. And sorry, this is the these reverse bias, this will lead to reverse bias leakage currents, and I have already explained about the band to band tunneling current. Then I have already discussed about the subthreshold leakage current. This is the expression for subthreshold leakage current. I am not going to discuss in detail about this expression, but you look at the key features of this expression. Number one is this current increases exponentially, drastically with temperature, because of the presence of temperature factor here, this factor, because of these two, this reduces, this becomes larger. So, leakage current increases drastically, exponentially with temperature. It also increases as threshold voltage is scaled down. Here is the threshold voltage. Whenever we are going from one technology generation to the next technology generation, you are reducing the threshold voltage, and as the threshold voltage is reduced, the leakage current increases. So, this is as a consequence, the threshold leakage current is heavily dependent on threshold voltage, and also it depends on the temperature. Another important observation is given here. You can see, because of as you are going from, say, you are going from one technology generation to next technology generation, you can see this is 1 micron, this is 0.8 micron, this is 0.6 micron. As I have told, the number of transistors in IC is increasing. As a consequence, this active power is nothing but the dynamic power that I have told, that is increasing. But the leakage power, which is the standby power, or you can see this static power, that is increasing at a much higher rate than this active power, and it has been found that you can see there was no botheration about leakage power or static power dissipation below 0.2, I mean when the device was bigger than 0.25 micron. That means when the technology is bigger, say 5 micron, 1 micron, these there was leakage current was very small, but it has increased. You can see as you go to 70 nanometer, you find the leakage current is larger than the leakage power dissipation is larger than the dynamic power dissipation, and as a consequence, leakage power is becoming a large component of total power dissipation, more than 50%. And reduction, particularly this has led to another important approach. You have to reduce the runtime leakage power. Earlier people used to reduce the leakage power only when the circuit is standby mode, because in those days the active power or dynamic power was very high. So when the circuit is standby mode, dynamic power is reduced automatically, but the leakage power reduction was not done. But now even when the circuit is in active mode, along with dynamic power, leakage power dissipation is taking place, and as a consequence there is a trend towards reduction of the runtime leakage power. Okay, now let us consider the degrees of freedom. So as I told, you have to reduce power dissipation. What you have to do here, particularly how you can reduce dynamic power dissipation is given here. So your low power design space is supply voltage. You can reduce dynamic power by reducing the supply voltage. As we have seen, the switching power dissipation has quadratic relationship with VDD. That means it is proportional to VDD square. If you reduce the supply voltage, obviously the switching power dissipation will be reduced significantly. Then physical capacitance CL, as I have told, then switching activity, that alpha. So these are the three parameters which you can minimize. That means optimizing power consumption invariably involves reducing one or more of these three parameters. And supply voltage has the most dominating effect on power dissipation because of quadratic relationship. As we have seen that short circuit power dissipation is proportional to VDD square. Switching power dissipation is proportional to VDD square. Short circuit power dissipation is proportional to VDD minus 2 VT cube, and as a consequence, reduction in the supply voltage leads to significant reduction in the dynamic power dissipation. Of course, leakage power dissipation is not shown here. Leakage power dissipation has to be controlled by reducing the threshold voltage. First, we shall focus on reduction of dynamic power reduction techniques. So various low power design methodology has emerged, and which can be applied at different levels of design hierarchy, starting from fabrication level to or system level to fabrication level, layout level. And we shall simply mention about some of the techniques and discuss some of the techniques which are used at different levels of design hierarchy. Say this one, a system level approach. System level approach is essentially based on hardware software trade-off. What do you really mean by that? Hardware software trade-off. Whenever you go for designing a VLSI circuit, you have to identify which part you will realize by hardware, which part you will realize by software. Because now same functionality can be realized by hardware or by software or by a combination of both. But it has been found that hardware based approach leads to faster circuit. However, it will be costlier in implementation, because since you are implementing in hardware, it will be costlier, and also it will consume more power because you have got the hardware is present there. On the other hand, software based approach is cheaper, slower, and consumes lesser power. That means whenever we are going for low power, we have to realize as much as possible by using software, as minimum as possible by using hardware. If possible, we shall try to implement by software rather than by using hardware. Of course, we should not compromise in performance. Performance is very important. Without compromising performance, you have to do this. So I shall consider a very important example. I don't know whether you are aware of the superscalar approach. Superscalar approach is an approach by which microprocessors are realized. Nowadays, all the microprocessors like Pentium, for example. Pentium is based on superscalar approach. What is done there? Inside the single processor CPU, you have got a number of functional units. Now, to keep the functional units busy, certain additional hardware is required, which is shown here. That means you have got x86 instructions, means X is the generic name, Intel processors, x86. It can be Pentium, it can be 486, 386, Pentium Pro. So x86 is the generic terminology used to represent Intel microprocessors. So these instructions are passed through a decode unit, where these instructions are decoded. As you know, Intel microprocessors, these x86 processors are based on CISC processor. CISC means complex instruction set architecture. So instructions are very complex. So they are decoded, then they are translated into a number. Each instruction is decomposed into simple operations, which are known as micro operations. And these micro operations can be executed with the help of different functional units. Since you have got a large number of function operations, they are sent to the dispatch unit, and dispatch units actually sends them to different functional units. And here it may so happen that you are doing those operations out of order. So you will require, that means functional units will do various operations like floating point, fixed point operations and so on, and then you will require a in order retire unit where those results will be combined, will be taken, and then results will be produced in order. That means the order in which instructions has been received here. And here all these things are implemented, this decode unit, translate unit, dispatch unit, in order redo unit, these are implemented by hardware, and these are very power hungry. And as a consequence, what we are doing here, exploiting instruction level parallelism. That means various operations which can be executed in parallel are exploited by performing them in parallel with several functional units. But this approach has led to very high power dissipation. Another approach is known as VLIW approach. VLIW stands for very large instruction word. So very large instruction word approach. In this case, it is based on compiler. What the compiler does, compiler will extract the various operations which can be executed in parallel. Then they form a bigger instruction and those instructions are obviously will be large in size in terms of number of bits compared to the instructions of those CISC processors. And they can be, once they are compiler, it generates these instructions in which, as you can see, you have got 4 different operations. Normally in an instructions you have got only one operations, but here as you can see you have got 4 different operations. So these 4 different operations are sent directly to different functional units. So you don't require those complex translation units, dispatch unit and unit. Only thing that you require is a sophisticated compiler. The compiler extracts the instruction level parallelism, identifies the parallelism, extracts the instruction level instructions which can be executed in parallel, then form a complex instruction, and then which they can be executed just like in a normal way. Fetch one instruction, execute them in order. So this is a in this approach, what is happening, this is a software based approach, and as you can see, there is a company known as Transmeta. You can visit their website, Transmeta's website. They developed a processor known as Crusoe processor. In this Crusoe processor, the processor is implemented by using this VLIW approach. However, what they have done, their input is, and what they do, they use compilers to form instructions, long instruction model called molecules, which can be 64 or 120 bits long, and a molecule can contain up to 4 RISC-like operations, simple operations, which are called atoms. That means 4 or 5 atoms will form a molecule. That means molecule is a single instruction of a VLIW processor, and which can be, these atoms can be executed in parallel, because you have got these execution units in a single processor. They can be executed in parallel. You can see this is a floating point unit, this is a integer unit, that means and this is a load store unit, this is a branch unit. These can be performed in parallel. And you may be asking, who actually is doing this compilation? There is a software known as code morphing software that mediates between this hardware and the Intel programs, that is your x86 instructions. That means BIOS, operating systems, various applications like your word processing and other things are in nothing but Intel instructions. Those instructions are are passed through. I mean, there is a software which receives those instructions that converts them into instructions of the VLIW engine. So here we are transforming from one instruction set architecture to another instruction set architecture with the help of this code morphing software. You may have heard of this term morphing. So here we are doing code morphing. We are translating from one instruction set architecture, Intel instruction set architecture, to the instruction set architecture of the VLIW processor. And this is how it is being done. And let's see the outcome of this. Here a program, that is a Pentium 3 processor, which is playing a DVD, and here, as you can see, this is the temperature profile. The temperature is rising 105.5 degrees centigrade. On the other hand, same program is being executed in Crusoe processor, which is implemented based on VLIW technique. The temperature rises to only 48.2 degrees centigrade. This is where the processor is. So, and in fact, I don't know whether you are familiar with that Intel 64-bit processor, that Itanium 64, is based on VLIW approach, in contrast to superscalar approach that is used by its predecessors. Those 386, 486, Pentium, Pentium Pro, all these processors were implemented by using superscalar architecture. But here there is a change. So Intel, there is a radical change, shift from in the architectural trend. In their Itanium, they have used this VLIW approach instead of using superscalar approach. Okay. Now we shall come to the second approach, that is, as I told, supply voltage is the most crucial parameter which can be used to reduce power dissipation. And because of quadratic relationship, a factor of 2 reduction in supply voltage yields a factor of 4 decrease in energy. And it has been found that theoretically the CMOS circuits can work up to 0.2 volt. However, nowadays the supply voltage has been reduced from 5 volt to 3.3, from 3.3 to 2.2, from 3.2 to 1.8. Nowadays most of the CMOS circuits are operating at 1 volt, although theoretical lower limit is 0.2 volt. Now let us see what is the outcome. As you reduce the supply voltage, as you can see here, the energy, which is power into delay, that reduces. And so we will always be interested in reducing the supply voltage to reduce power dissipation, but unfortunately as you reduce the supply voltage, you can see the delay of the circuit increases. particularly when the supply voltage becomes closer to the threshold voltage, the delay increases exponentially. The reason for that is that that delay has a relationship which is proportional to 1 by VDD minus VT square. And as a consequence, when VDD and VT and VDD are very close, then what will happen? That denominator will become very close to 0. So the power dissipation will be very high, and that is why we cannot really reduce power dissipation, power dissipation simply by reducing the supply voltage. We have to see such that delay is not reduction in increase in delay means what? Reduction in performance. So without compromising in performance, we have to reduce the supply voltage. That is the challenge of low power design. And there are various approaches which has emerged. First one is known as static voltage scaling. In this static voltage scaling, what you are doing, different blocks or subsystems are given different fixed voltages at design time. And in multi-voltage scaling, what you are doing, this is extension of static voltage scaling, where two or few fixed voltages are applied to different subsystem at different instance of time. That you are doing, that means here it is kind of dynamic. When you are doing at design time, doing the design at design time, also at run time you can apply different voltages to different subsystems to reduce supply voltage, power dissipation. Then finally you have got dynamic voltage and frequency scaling. This is an extension of the multi-voltage scaling, where a large number of voltage levels are dynamically applied for different workloads. Later on I shall discuss these techniques in detail. Now one very important approach for supply voltage scaling is device size scaling. What is device size scaling? As you know, when we are going from one technology generation to another technology generation, you are essentially reducing the dimension of the devices. What are the dimension? This is the schematic diagram of a MOS transistor. So this is the this is the source, this is the drain, this is the gate region, channel region, this is the oxide, silicon dioxide layer. You can see you are reducing silicon dioxide thickness by factor S, which where S is greater than 1, maybe 1.2 or 1.3. We are increasing the doping concentration to of the source and drain regions. You are reducing the length, channel length. This is the 3 channel length by factor S. We are also reducing the width. That is, you are also reducing the depth of penetration of the device. That is your 4, and also you are reducing the width, and of course you are increasing the substrate doping 6. What is the outcome of this device size scaling? In constant field scaling, what you are doing, you are reducing the various dimensions. As a consequence, capacitance is decreased, current is decreasing. Current is decreasing because you are reducing the supply voltage. You are reducing supply voltage as well, which is not shown here. Supply voltage and threshold voltage by the same factor S. And as a consequence, your capacitance is reduced because length, width, and all these factors are reduced. Length, width, thickness of the silicon dioxide, and as a consequence, gate capacitance is reduced because this is the MOS capacitance you can see. So capacitance is reduced, drain current is reduced by factor S. Power dissipation is reduced by a factor of S square, and power density fortunately remains same. Delay reduces, energy reduces by a factor of S cube. So you see the benefit of this device size scaling. And in fact, you may have heard of Moore's law. Moore's law is being followed for the last 3 decades. So by Moore's law, what is happening? Dimensions are reduced, and as a consequence, you are able to put more and more transistors. The performance is increasing, speed is increasing, power dissipation is also reduced, but this is the dynamic power dissipation. In fact, this has helped Moore's law to survive this device size scaling. So what we find here, as we are because we are reducing the dimensions, we are and we are able to reduce the supply voltage and the threshold voltage, that has led to increase the performance without increasing the power dissipation, rather power dissipation is reducing. So this is one way of reducing power dissipation, although you are doing supply voltage scaling. Okay, and this is, I can see the another way of showing the scaling. This is how the various dimensions are scaled and over the years starting from 1991 to 2007. Now we shall consider another approach, which is architectural approach for reducing supply voltage. You are familiar with parallel processing. In parallel processing, what you do? You duplicate the resources to get more and better, higher and higher performance. That is the basic idea of parallelism. That means parallelism is commonly used to achieve higher performance. Here I shall show how parallelism can also be used to reduce power dissipation. That means here parallelism for low power, not for performance but for low power. How it can be done, I shall explain. So here the key approach is to trade area for power while maintaining the same throughput. Here we are not trying to improve the performance, we are trying to maintain the same performance. That means throughput is kept same. However, we are increasing the area because of parallelism. So why it is happening? It is happening because, you know, as you increase the parallelism, you can, if you want to perform at the same rate, want to keep the throughput same, you can reduce the supply voltage because delay will be more. So since we are doing twice, you can do that. And if you reduce the supply voltage by twice, you know, power dissipation will become 1/4, but you have already duplicated, so you will get a power reduction by 1/4. This will be very clear with the help of this example. So this is a very simple example. We have a 16-bit adder. You can see you are applying it is operating at a frequency f ref, reference frequency. So what will be the power dissipation? We know the switching power dissipation will be equal to C reference into V reference square into F reference. V reference square is the supply voltage, and this is the estimated dynamic power of this circuit. It is operating at reference voltage V reference and operating at frequency F reference. Here switching factor is not shown. Of course, switching factor is there. Actually, C reference includes the capacitance and the switching activity. That is why it is called switching capacitance or switched capacitance. Now, this is operating at 100 megahertz. Now, let us see, we have duplicated it. So, we have used parallelism, two circuits are there, but what we are doing here, this circuit is operating at half the frequency. So, V reference by 2, V reference by 2. So, it can it is operating at half the frequency, F reference by 2. So, this is operating at half frequency, this is also operating at half frequency. That means that delay can be increased. Delay can be increased means we can reduce the supply voltage. So, we have reduced the supply voltage and it is operating at half the frequency, this is also operating at half the frequency. And since we are doing the multiplexing, here the data rate is same as the previous case, because here we are getting at f ref. That means half of the processing is done here, half of the processing is done here, then you are multiplexing as you do in case of your pulse code modulation PCM. So here you are doing multiplexing. So what is the outcome? Outcome is, you can see the now in this parallel approach, your capacitance is increased because you have duplicated the circuit. Not only duplicated, you have added one multiplexer. So the capacitance has increased by a factor of 2.2. However, you have reduced the supply voltage by 2. You have also reduced the clock frequency by 2. We have seen that clock frequency is reduced by 2, supply voltage is reduced by 2, keeping the throughput same. What is the outcome? Now the power dissipation is 0.227x. That means without supply voltage scaling, you could have improved the performance. This is no parallelism for higher performance. You could have increased the throughput by 2, but in that case power dissipation will be 2.2 times of the original case. But here what we are doing? We are doing parallelism for low power. So power dissipation is reduced by, you can see, 0.277. So significant reduction in power dissipation is taking place here. And this approach has been used in multi-core architecture. You can see in multi-core architecture you can keep on increasing the number of cores, and if you are interested in having the same throughput, you can simply reduce the frequency and supply voltage and reduce the power dissipation. And in fact, nowadays you may be observing that now many processors are being implemented by using multiple cores. Quad duo, dual core, quad core. In fact, low power is a driving factor towards this multi-core architecture, and this is the basis for that multi-core architecture. That means using multiple cores, what we are doing, instead of increasing the frequency, we are keeping the frequency same, but using parallelism, we are trying to achieve the performance, but power dissipation is lower, as I have demonstrated with this a simple example. Is it clear? Now you can use also pipelining to reduce power dissipation also. You can see what is pipelining. Pipelining is you can divide a task into subtasks. So what we have done here, we have divided 16-bit addition into two 8-bit additions, and you can see here this is one 8-bit adder and this is another 8-bit adder. Of course, you have to use latch to store the intermediate results whenever you go for pipeline implementations. And in fact, all modern processors are having this pipeline implementation. So whenever you go for pipelining, as you can see, you can keep the frequency same, but since here you are using 8-bit processor, obviously delay will be half that of 16-bit processor, and so you can reduce the supply voltage half if it is operating at the same frequency. So here also you can reduce the supply voltage by half, and that means since the delay, this is 8-bit adder, here also it is 8-bit adder and operating at the same frequency as this original circuit, you can reduce the supply voltage by half in pipeline processor, and as a consequence the effect is, in pipelining, another advantage is that capacitance, switched capacitance does not increase much, because you can see you have got 8-bit adder. So these two together forms the 16-bit adder. Only you have got additional latches. That's the overhead increase in pipelining. So it is 1.15 Cref compared to reference capacitance. It is only 1.15 times. However, the supply voltage is now V reference by 2. Of course, the frequency is same, and if we multiply all these things, you get 0.28 P reference. So pipelining also can be used for improving performance in this way. If we don't do supply voltage scaling, you can increase your performance 2 times, which were done earlier. So pipelining were used earlier to improve the performance at the cost of higher power dissipation, but now we are doing it pipelining for low power. So keeping the throughput same, as I told you, that is the challenge. We don't want to compromise in performance, that means maintain the same throughput, but power dissipation has to be reduced. That is what we have done here. So you can see here power dissipation is now 0.28x compared to 1x of the reference circuit. And of course, you can combine pipelining with parallelism. You can see here this is 16-bit and another 16-bit. So parallelism and pipelining have been combined together, and you can get more benefit by this. You can see here you can get only roughly 11% power dissipation with respect to the original reference circuit by combining pipelining and parallelism. Okay, so this is architectural approach for supply voltage scaling. You can do it at the circuit level. So this is a circuit, combinational circuit between two resistors, you can say. So you can see this is the critical path and this is the non-critical path. Obviously, you cannot really afford to reduce the, increase the delay of the critical path. So these gates can be operated at higher supply voltage. On the other hand, these gates which are on the non-critical path, they can use lower supply voltage because their delay will increase if you operate at lower voltage, as you have seen. But as long as their delay does not exceed this 10 nanosecond, you are safe, because you know that overall delay from here to here should not exceed the critical path delay. As long as that is not violated, you need not bother. So what we are doing here, we are using two different supply voltages, higher supply voltage for the gates on the critical path and lower supply voltage for gates on the critical path. So you can do kind of clustering. You can cluster gates which are on the critical path, apply high supply voltage because they should be fast. So high supply voltage is required, and you apply lower supply voltage to gates on the non-critical path, and because you can afford to increase their delay by lowering their supply voltage, and as a consequence overall power dissipation will be lower. Then coming to the third approach, this dynamic voltage and frequency scaling. Here you can see we can, normally a processor is not always 100% busy. By that I mean, you will find that whenever using your laptop or desktop, you will find that if you look at, you will find that CPU utilization is 10% sometimes, 15% sometimes 50%. But if they operate at the same frequency, if they operate at the same supply voltage, power dissipation will take place. So what you can do, you can adjust the frequency as well as the supply voltage according to the workload. If the workload requirement is low, 10%, you can reduce the supply voltage and frequency together, because we have seen that if you reduce the frequency, obviously the performance will reduce. So as you are able to reduce the frequency, say from 700 megahertz to 200 megahertz, this processor will operate at lower supply voltage. So what you do, you reduce the frequency. Not only if you only reduce the frequency, then power dissipation will decrease at linear rate. That means you are not doing supply voltage scaling. You are only doing frequency scaling. You are reducing the clock frequency. That will also lead to reduction in power dissipation. But if you reduce the supply voltage along with frequency, you can see the relative power dissipation is significant. For example, at a particular instant, if the 200 megahertz clock frequency satisfies the workload requirement, then you can operate it at 1.1 volt, then power dissipation will be roughly 12% of the original case. So this is the basic idea of this dynamic voltage and frequency scaling, and it is a runtime dynamic power reduction technique. And how you can do that? You can see this is the basic scheme for dynamic voltage scaling. This is a processor. You require a processor which will operate at different voltage as well as at different frequency. That is one requirement. You should be able to adjust the voltage. In our institute, many people are working on developing DC to DC converter. So you will require a DC to DC converter which will reduce where the supply voltage can be adjusted. You can generate different voltages. So you will require a variable voltage power supply, and you will also require some circuit which will change the frequency. That you can do by using phase lock loop and divider. So you require what? You require a variable voltage processor, DC to DC converter, and part of this workload converter you have got a different frequency generator. Now you can see various tasks are coming from different sources. Here I have shown that it is a server. Tasks are coming from a number of clients. So, tasks are coming, then it is being scheduled and with an average rate of lambda, and depending on that workload can be predicted, workload can be monitored, and based on the past workload you can predict what will be the workload in the next time instant, and based on that prediction you will generate a clock frequency, you will also generate a supply voltage, and that is the basis for this dynamic voltage and frequency scaling. And this is the schematic diagram of a DC to DC converter. Here as you can see, you can generate different voltage, variable voltage with the help of a fixed reference voltage, with the help of a pulse width modulator, low pass filter and a electronic switch. This switch is obviously realized with the help of some MOS, I mean some kind of gates, some kind of transistor, MOS transistor. Okay. So, this is the basic approach, and we have seen that there is a significant reduction in power dissipation whenever you go for this dynamic voltage and frequency scaling, and nowadays these are being used in many systems. Okay. Coming to another technique which is known as power management. In power management, what you can do, you can shut down some parts of the circuit whenever they are not needed. As I was telling that if whenever there is no user, that screen can be turned off. You can reduce other power hungry components, say if you are not using multimedia processor, if you are not doing multimedia processing, you can shut down the multimedia processor. For example, in your cell phone, if you are talking, there is no need to use keep the camera portion on or other portions on, only that transmitter, or whenever you are communicating, transmitting, only transmitter portion can be turned on, receiver portion can be turned off, like that. So, in this way different portions can be turned off and you can have power savings, you can make it on and off, and if you if it is on for 50% time, then we say that 50% is a duty cycle, or there is a power reduction of 50%. Now, what you can do, this power management approach can be combined with dynamic voltage and frequency scaling to have significant still power, I mean still lower power reduction. For example, this part, this line is corresponding to traditional power management, linear. However, by using dynamic voltage and frequency scaling, where you get quadratic reduction in power dissipation, you can see, but you cannot go below certain point. You know that processors will operate up to certain voltage. A processor will operate maybe from 1.2 volt to 0.7 volt. The supply voltage cannot be reduced below 0.7 volt, but that means you have reached this point. After that, what you can do, if you do not use dynamic voltage and frequency scaling, if you reduce the workload, your power dissipation will be like this. But if you do power management, still you can linearly reduce from this point to this. So, what you are doing, you are combining dynamic voltage and frequency scaling with power management to reduce the power dissipation significantly. You can also use bus encoding. Whenever you are communicating through a bus, normally bus is off chip. When it is off chip, capacitance is very large. So, there is heavy dynamic power reduction. So, whenever you are communicating through a bus, you can reduce power dissipation by proper encoding. What is the basic what is the basic approach here? You can do, you can do coding two ways. You can remove undesired correlation among information, which you do in case of encryption, or you can do introduce control correlation. So, if you have control correlation, that means correlation means what? The present data is correlated with the next data. That means minimum change. Minimum change means lesser dynamic power dissipation. If 0 remains 0, in the next time, if it does not change from 0 to 1, there will be no power reduction or power dissipation. That is what is being done in coding. You are introducing control correlation, and there are various approaches one hot encoding, gray coding, bus inverse coding, T0 encoding. I shall very quickly show you these approaches, particularly this has applications in multi-core SoC architecture. So what you are doing here, normally sender directly sends to the receiver through the communication in bus. This is the bus. What we are doing, we are introducing an encoder and a decoder in between. And as you do that, different types of coding possible. One is redundant. Redundant coding means that M will be more than N. M will be greater than N. That means you are adding more number of lines. So it is redundant coding. It can be non-redundant if M is equal to N. That means if N is the number of data lines, it can be address lines also, does not matter, number of lines coming from the center, and here if it is also N, then it is called non-redundant coding. Now this depending on the type of encoding you are using, you will require either it can be purely combinational circuits, decoder and encoder, or you may require memory to implement the encoder and decoder, as we shall see with our examples. So one hot encoding, what we are doing, we are essentially having only one bit. That means say if your if the code is say changing from 001 to 010, normally this 001 is coded as 3, means it will have 8 bits. 001, 2 is 00000100. So you are having, that means here one hot coding means only one bit is 1 in that code. This is the code, this is the data. So you are here, it is N is equal to 3, here it is M is equal to 8 to the power 3. So this is how you are doing the coding. 001 is coded to 00000010. That means first bit is 1, that means 001 means first bit is 1, 010 means second bit is 1. Now if you changes from this to this, there will be 2 bit changes, but if it changes from say 111 to say 000, here what will happen, 111 will be 01000 0000 and 000 is 0001. So you can see when it is switching from here, there will be 3 bit change, but here there will be only 2 bit change, always 2 bit change as you go from one code to another. So this is the basic idea of one hot encoding. So using one hot encoding, it is possible to reduce power dissipation, but the number of lines increases. So it is not very good approach of encoding. So that's why another approach is to use gray coding. In gray coding, this is the binary code and this is the gray code. You can see if you go from one bit to next bit, only one bit change. Say this is the binary code. Here there may be, say here there is 4 bit change, but here again only 1 bit change. So if you coded in this form, and if the data comes in a correlated manner consecutively, then there will be only 1 bit change, not 3 bit change or 2 bit change or 4 bit change. So this is the basic idea of this gray coding. We have seen whenever you are executing a program, you store your program in consecutive memory locations until you have a branch or subroutine call or jump. In such cases, there will be significant reduction in power dissipation if you use gray coding. So here, as you can see, gray coding has been used. Particularly it is useful when data is sequential and highly correlated, like instruction address, that means address bus, and there was simulation performed. As you can see, this is the simulation on, different programs were run, and this is the number of bit transitions per instruction executed. A program will consist of large number of instructions. So total number of transactions by the number of instructions is the number of bit transitions per instructions. That is shown here whenever it is binary coded, and whenever it is gray coded, there is significant reduction, as you can see, almost half. So you are reducing the switching activity, and this will lead to reduction in power dissipation. However, it has no impact on data bus. The reason is data is highly uncorrelated, because you have stored haphazard data and they are not correlated. and as a consequence you do not get similar kind of benefit on data bus, as you can see in this table. So, sometimes in fact you can see there is sometimes there is reduction, but sometimes there is increase in the switching activity, which is represented by number of bit transitions per second. And this is the another technique is bus inversion coding, where what you can do, you can use an extra bit to say whether, say for example, you are sending n bits. Whenever you are sending another next sequence of bits, then if the Hamming distance between the n bits and the next n bits is the is more than n by 2, then you can send the complement of it, then the Hamming distance will be less. That is the basic idea. But how the other side will know? You have to send one additional line informing whether you are sending the original data or inverted form of data. That is the basic idea of bus inversion coding. And bus inversion coding has been widely used. You can see there is reduction possible up to you can have, say this is 0.6. However, depending on the number of bits and the performance depends in bus inversion coding. Another important coding technique is T0 coding. What is T0 coding? In T0 coding, zero transition coding. So, the other side is now intelligent. If you are sending consecutive data, you do not make any changes on the bus. Only tell the other side that increase, 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 keep on incrementing. That is what is being done in your T0 encoding. So, what you are doing, if the only it is increment by a factor of s, as you know, in case of instruction, present instruction and next instruction will be maybe difference in address will be 4 or 8 depending on the number of, say in a 32-bit processor, the present address and next address will be 4 bytes apart. So, you keep on adding 4. So, this is what is being done here. So, if you keep on adding s is equal to stride, that is 4, as long as it is simple increase. Of course, if it is not so, whenever subroutine call takes place, branch takes place, interrupt occurs, then you have to send the original data, and in that case there will be transitions. So, asymptotically the number of transitions approaches 0 in this T0 encoding if you keep on sending consecutive addresses. That is why it is very effective in your address encoding. Coming to reducing the glitching activity, I have told that because of delay, glitching power dissipation occurs. What has been done here, you can see the signal is reaching here little later than this signal. As a result, glitching power dissipation is occurring here, and similarly this signal is reaching later than this signal. Glitching power dissipation is taking place here, which I have explained earlier. Instead of realizing the circuit in this manner, you can realize it in a balanced manner like this. So, whenever you realize in this balanced manner, obviously the signal will reach here and here at the same time. So, the glitching power will be reduced. That means, instead of realizing in a chain manner, you realize in the form of a tree. That will lead to reduction in the glitching power. Not only it will lead to reduction in the glitching power, it will also reduce the delay, because the circuit is now balanced. Here you can see path delay is 3, here it is path delay is 2. So, this will be very useful in low power applications. Another approach is clock gating. As I was mentioning, whenever a particular part of the circuit is not is not active, then for example, this is you are loading some value in this latch. Normally if this global clock is applied here, and every time data changes take place, so unnecessarily transitions occurs. What you can do, you can identify the condition when data change is not necessary. You can do clock, then stop this clock you are doing clock gating, does not allow this clock to reach these latches. So, there will be no change, no transition will occur, there will be no power dissipation. This is the basic idea of clock gating, which is used to reduce dynamic power dissipation in sequential elements and local clock drivers. Because clock drivers nowadays consumes heavy power, 50% of the total power is dissipated in the clock tree, and by using clock gating, as you can see here, only leakage power dissipation is taking place. Dynamic power dissipation is removed when we are doing clock gating. So, you can reduce the power dissipation by clock gating by using this type of circuit. And then you can use different types of logic styles like static CMOS, dynamic CMOS, fast transistor logic. I do not know whether these things have been introduced to you. No. Anyway, so these logic styles you will study later on, and by using these logic styles, this is the static CMOS logic style, this is the dynamic CMOS logic style, and this is the fast transistor logic style. I am not going into the details because now it is not possible to go into the details of this, and I am going to directly to the experimental result. You can see nowadays most of the circuits are realized by using static CMOS, because most of the CAD tools are available only for static CMOS. CAD tools are not available for dynamic CMOS and fast transistor logic circuits. One of my PhD student did some research work on this, and they found that the benchmark circuits, if they are realized by using dynamic CMOS circuits and fast transistor logic circuits, you can see there can be reduction in the area, reduction in the delay, and reduction in the power dissipation. This is using dynamic CMOS, and this is by using fast transistor logic circuits. You can see there is significant reduction in the area, significant reduction in delay, and also in power dissipation. So, if you consider power delay product, that is your energy, that reduction is significant. Same thing is shown in these bar graphs. Now, we shall come to the leakage power reduction technique. So far, we have discussed the dynamic power reduction techniques. We shall come to the reduction of leakage power reduction technique. Okay. So, I shall take maybe another 15-20 minutes. Okay. You can see leakage power is heavily dependent on the threshold voltage, and normally we have seen whenever we do dynamic voltage scaling, I mean, then also the threshold voltage remains same, but as we are going from one technology generation to the next technology generation, we have seen that supply voltage is reduced, threshold voltage is also reduced. So, what is the impact? Let us see. As the threshold voltage is reduced, delay reduces, which is attractive, which we want. But as the threshold voltage is reduced, you can see the leakage current increases exponentially. This is in logarithmic path. This is a log linear plot. So, you can see the leakage power is increasing significantly as we reduce the threshold voltage. Now, is there any way by which we shall try to get best of both the worlds? By best of both the worlds, I mean we shall try to achieve the same performance, but at the same time reduce the leakage power. There, what we shall do, we shall make use of multiple threshold voltages. How we shall explain? This shows the importance of leakage power. You can see the leakage power was not predominant below 0.35 micron, but now it is increasing exponentially, and we must stop at this point somehow. What is somehow? I shall discuss by using suitable technique. You see the leakage power, you can see whenever you use low threshold voltage, delay is small, you get high performance, but leakage power is high. On the other hand, whenever you use high threshold voltage for the same transistor, your delay increases, but leakage power is less. Normally threshold voltage can be in the range of 0.2 VDD to 0.5 VDD. That means if the VDD is 1 volt, threshold voltage can be in the range of 0.2 volt to 0.5 volt. So, when it is 0.2 volt we call it low VDD, low threshold voltage. When it is 0.5 volt we call it high threshold voltage, and that will lead to significant difference in performance and threshold voltage, I mean leakage power, sub-threshold leakage power. And various approaches have been developed for threshold voltage scaling, by which you can reduce the leakage power, and particularly there are different ways of reducing the controlling the threshold voltage. You can use multiple channel doping, multiple oxide thickness, multiple channel length, multiple body bias. These are the approaches by which you can realize different threshold voltages in a single circuit, and these are the various approaches which will make use of these techniques, which I shall see. I mean, some of the techniques I shall show you. This is a technique where variable threshold CMOS, known as VT CMOS. What is being done here? You see, normally what you do, this source is connected to substrate. Here also this well, this is N well, this well is connected to VDD. But what you have to do to realize VT CMOS circuit, you have to disconnect here, you have to disconnect here. That means substrate as well as the well, N well, has to be given different voltage, and that is being shown here. That means what you can do, when the circuit is in normal mode of operation, you adjust the body bias, that means the substrate bias and well bias, to maybe 2 volt. 2 volt means as if we have sorted, and here also as if it is ground, that means as if it is ground. So, threshold voltage will be 0.2 volt and it is minus 2 volt. Low threshold voltage, you will get very good performance. Now what you do, you adjust the body bias, you make it 4 volt here, that means this is 4 volt and this one is minus 2 volt. And as you do that, the threshold voltage changes to minus 6 volt for PMOS transistor, and for NMOS transistor 0.6 volt, and that you do in the standby mode. Standby mode you do not require high performance, but in the leakage power will be reduced significantly. We have seen there is exponential dependence on on threshold voltage, on the, and that subthreshold leakage current depends exponentially on the threshold voltage. So, as you reduce from 2 volt to 0.2 volt to 0.6 volt, you can see several orders of magnitude reduction in leakage current will take place. That is what is being done in this variable threshold CMOS approach, VT CMOS approach, and this is being done nowadays in many cases. But here you can reduce only the standby power. That means only when the circuit is standby mode, then you are able to reduce the leakage power dissipation. When the circuit is active, that time obviously you want performance. So, your threshold voltages will be low, 0.2 volt, minus 0.2 volt, and leakage current will be high. So, runtime leakage current is high, but standby leakage current is less. Another approach is you can insert additional high VT transistors in series. Here you can see in between the supply voltage and the virtual supply voltage, you have applied a high VT transistor. Here also you have used a high VT transistor, and these high VT transistors are on in the normal mode of operation. So, when the normal mode of operation, the high VT transistors are on, and the circuit which is realized by low VT transistor, this portion by using low VT transistors, gives you good performance. So, you get good performance in the normal mode of operation, and whenever you are when the circuit is in the sleep condition, sleep means standby. So, then you make this transistor off, this transistor off, then what will happen, the leakage current that will be passing through this circuit will be very small, and this is known as empty CMOS approach, multi-threshold CMOS. That means you are making use of multiple threshold voltage transistors. These transistors are fabricated along with these your circuit, which is realized by using low VT transistors. And this is the performance. You can see delay is obviously there is small increase in delay by whenever you go for empty CMOS, but that delay is not very significantly higher on, that means it is very close to low VT CMOS transistor. Then energy dissipation is also very low in empty CMOS approach. This has been proved by simulation. Not only that, these people, these S. Muthu and et al., they realized practical circuits by this approach, and they had shown significant reduction in power dissipation can be done. Although empty CMOS can be easily implemented by using existing circuits, this reduces, but it reduces only the standby power, as you have seen. It does not reduce the runtime power. And also these those additional MOSFETs that you are introducing as slip transistors, they will occupy some area, they will also introduce some delay. So extra moreover there will be some memory circuits which will create problem whenever you go to standby mode. So another approach has been proposed which is known as dual VT assignment. In this approach you will see that there is reduction in runtime power, runtime leakage power, which does not take place in case of your in the previous two cases. What is the basic approach? Here the basic approach is again same as that dual VDD. Here what you are doing, you see some of the gates are on the critical path, some of the gates which are not on the critical. These gates which are in dark color, they are on the critical path, and these gates which are not on the critical path. So what you can do, you can assign high threshold voltage to realize, high threshold voltage transistor to realize gates on the non-critical path, and low threshold voltage transistor to realize gates on the critical path. And by that process what will happen, your leakage power will reduce for the gates on the non-critical path. Of course, the gates on the critical path will have same leakage power as the original case, but you have many gates on the non-critical path. There significant reduction in power dissipation will take place. As you can see here, 0.25 VDD is the assigned to gates on the off critical path, and 0.2 is the threshold voltage of the critical path. However, as you increase the threshold voltage, high VT threshold voltage, then some gates you cannot assign high threshold voltage. So there is a kind of optimization. Here you have to identify a high threshold voltage where the leakage power reduction is minimum, and which you can assign to gates on the non-critical path. So some research was performed, an algorithm was developed. This is the algorithm by which you can identify the gates and the high VT threshold voltage that you can apply to the gates on the non-critical path, and you can reduce the leakage power significantly. Some of my students did some work in this area, and they got significant reduction in leakage power compared to earlier approaches which I have shown you earlier. So instead of 69% reduction, my students got 82.82% reduction in leakage power by assigning high threshold voltage to the gates on the non-critical path. And how this is achieved, you can see in the previous case the number of transistors which are assigned high VT is lesser than the number of transistors which are assigned higher VT in this particular approach. As a result, you can get a more reduction in leakage power compared to the previous approach. So these are shown in the, same things are shown here with the help of a bar graph. So here you can see by using single VT, low VT, this is the leakage power. Whenever you use dual VT, this is the leakage power reduction. So significant reduction in leakage power take place whenever you go for dual VT approach. And so it has compared single low VT, dual VT, earlier, and dual VT new one. So dual VT new one, that is the proposed which have been done by some of my students. There you find there is significant reduction in leakage power compared to the earlier approach, as well as the original circuits which is realized by using low VT. So here we see we don't reduce the we don't compromise the performance. because we have seen that we are not exceeding the delay of the critical path, but only the delay of the gates on the non-critical paths are increased by assigning high Vt, and as a consequence we are able to reduce the leakage power. So, here you have got some of the publications which I have shown in this, which I have explained in my lecture. So, we have come to the end of this lecture, and so let us summarize what we have discussed in this lecture. We have seen that low power is very important in the present day context because of various reasons, because of high performance, and because of to reduce the cost of cooling and packaging, to reduce the to improve the reliability, to have lesser impact of the environment. And we have seen there are two main sources of power dissipation. One is dynamic in nature when the circuit is active, another is static power dissipation when the circuit is in standby mode. So, we have discussed a number of approaches to reduce dynamic power dissipation, primarily by using supply voltage scaling, but without compromise in performance, by using clock gating, by using various other approaches. Similarly, we can reduce the leakage power essentially by controlling the threshold voltage, and we have seen approaches where particularly that VT CMOS and MT CMOS approach, where reduction of standby leakage power takes place, when that means when the circuit is in the standby mode. On the other hand, dual VT based approach is used where the when the circuit is both in running condition, active mode, as well as in standby mode. So, that is why this dual VT approach is very attractive. So, in about 1.5 hours, I have tried to give a glimpse of low power design methodology. I offer a full-fledged course on low power circuits and systems. It is I take about 30 to 35 lectures to cover the entire thing, which I have tried to cover in say maybe 1 hour 40 minutes or so. Obviously, it is an overview lecture. Thank you very much.